Ladies and gentlemen, dear colleagues, good morning. Welcome to our closing session of the Terrain Networking Conference 2008. It's my privilege to announce our final keynote speaker, Huub-Jan van Langevelde from Joint European Institute for VLBI, who is actually an astronomer, and I'm really glad that our conference today will be closed by, let's say, a demanding user. So without further delay, please, the floor is yours.
Thank you. Thank you. (2009) next year will actually be called the Year of Astronomy. The universe is yours to discover. It's commemorating Galileo's discovery of the moons of Jupiter in 1609, when he pointed the telescope at the heavens. This result he quickly published in 2010, and following that there was important work by him on the appearance of Venus, which supported his view of the Copernican system. This is a theme that has been continuing for 400 years, and we think we are in a golden age of astronomy, and this is made possible by innovating and advancing instruments all the time. That principle continues until today. Every time we build new instruments, we discover new things, often things that we didn't plan to discover. 2008, so this year, in that sense is actually more important. It is 400 years of telescopes. And it's actually not very far from here, north in the city of Middelburg, where the patent was requested for the first telescope. The story is a bit obscure, as there were several Dutch people who claimed to have invented or patented the telescope. It probably was an invention, or rather a development, first made by this lensmaker Zacharias Janssen, but his neighbor, this Mr. Lipperhey, went actually to The Hague to ask for the patent. So this enabled the discoveries. Of course, this device was first used in the war. This part of the Netherlands was actually occupied by the Spanish, and a lot of people had fled to the north, flourishing the cities there where the invention was made. So it was first presented as a war instrument, but soon later it became a scientific instrument. Galileo did not buy one of these telescopes. He heard about it and he made his own. And this qualifies, in my opinion, Galileo as a true astronomer. I've heard it here this week as well. Really, astronomers really like to do things themselves. They really want to build their own instruments, understand what they do, and make the discoveries. He also did something that I still try to remind my students of. He published quickly. In fact, there are stories that he was not the first person to observe the Galilean moons, but he was definitely the first one to write up his discovery and the importance thereof. So, in my talk today, I will try to explain to you what is radio astronomy, what is VLBI. I will continue to tell you how, with eVLBI, the network is basically becoming the telescope, being the demanding user that you want me to be. And then talk about global connectivity and, in fact, introducing the demo, which is actually breaking new grounds and is running upstairs in the demo room. I will try to introduce that here, so you have the background knowledge to go there and really appreciate what's going on. I will show you some science results, explain to you why it is important that we do this way, and I would like to show you in the end where this is going and what the future is of our branch of science. Okay, before I do that, I'd like to explain some of the acronyms and give credit to all the organizations that are involved. VLBI stands for Very Long Baseline Interferometry. So that's basically a technique in which you construct a telescope which allow you to study the heavens. We do this in the collaboration called the European VLBI Network, which is a consortium of telescopes around Europe and actually beyond. We also have telescopes in China participating as well as in Puerto Rico. And often we observe with our partner organizations in Australia or the US in this VLBI technique. As the introduction said, I'm from the Joint Institute for VLBI in Europe. It says the Netherlands on the introduction slide. It's based in the Netherlands, but it's actually funded largely by science councils in a number of participating countries. Again, most of them in Europe, but also in China. And then finally, I will show here mostly results obtained in the EC project Express, which was funded and started in 2006 and has as its partners most European radio telescopes, some very remote radio telescopes, and a number of the global European and local NRANs. So where do I point to? Okay. So before we go into the talk, I would like to briefly try to follow this link. And I hope you are not going to try to decipher where this is going, because if we all do this, we probably destroy the ongoing demo that's upstairs. So the demo is actually really happening in Dwingelo in the northern of the Netherlands, where data from telescopes all over the world is streaming into a hardware supercomputer, which is at the core of our VLBI operations. And what you see on the screen here is the very colorful picture is the total data rate that has been coming into that to that place over the last hour. It will continue for 2 more hours, so you have every chance to go upstairs and witness this in more detail. To the left, you see a map. Bottom, you see a map of the telescopes that are connected. Right is one webcam view of one of the telescopes. And the top right tells me, and I will explain later in this talk, that the demo is actually proceeding successfully, and we are getting detections from cosmic sources by telescopes connected on the internet. If you can take me out of the web browser now, I will try to explain to you what VLBI is and how it works. Okay, so radio astronomy. It's not about listening to the stars. When we have children visiting our premises, we say, oh, okay, these big telescopes, they listen to the stars. But that's not really what's happening, of course. It's electromagnetic radiation, just as light. We're just going to the low energy, long wavelength end of the spectrum. And when we talk about radio astronomy in this talk, we're talking about wavelengths of say, a few millimeters to up to a meter. And of course, that is a billion times longer than the wavelength of normal optical light. So if you turn on your radio to listen to the news, what is happening is that electric currents in a wire, a big wire somewhere, are used to encode voice or music, and your little radio device can decode that as well. To listen to the news, to listen to the traffic information. So there's also natural radio emission, and hot electrons that also move at great speeds, which are accelerated in between the stars. They radiate radio emission naturally. And if we build big telescopes and point them into the sky, we can actually discover these electrons in between the stars. This is a picture of the Milky Way showing that radio emission comes from everywhere, and the other is an example of a violent radio source, a black hole that is spinning up material to a point where it gets so hot that it will emit very bright radio emission. So this is not an old science. Where Galileo did his first telescope 400 years ago, the radio astronomy is still waiting for its first century anniversary. It was actually discovered by accident by this guy on the left top called Jansky, who was trying to do some research in why sometimes cross-Atlantic communication was bad. And he discovered that there was a source of radiation coming from the Milky Way. And this was largely ignored by most professional astronomers at the time, but picked up by this guy on the right bottom, a radio astronomer, amateur, who built the first, what we call now, what we think is a normal-looking radio telescope, to try to figure out where the galactic radio emission was coming from. His name was Groten-Reber, and he is really the Galileo of radio astronomy. So what do you do if you want to look at the sky and discover radio signals? You have to build a big telescope. Why do you want to build a big telescope? There are two reasons for that. The first is sensitivity. If you want to make out the extra noise that the electrons in the interstellar medium produce on top of all the thermal noise that is coming into your beam anyway, you have to build something big. The bigger the telescope, the more sensitive it is. There's a second reason to build telescopes big, and that is we're dealing here with very long wavelengths. And in order to distinguish things on the sky, to get some sort of resolution, you have to build a large diameter telescope. So we have such a telescope in our back garden. This is the institute in Dwingelo where I work. There is a telescope in the back garden that is 25 meters across, and it used to be the biggest telescope in the world in 1956. With such a telescope, you can distinguish things on the sky which have a larger area than your eye can make out in the optical. So, in some sense, this is a very sloppy telescope. It doesn't magnify anything. Because if you want to go to the same resolution as we can do with an eye or with Galileo's telescope, we would have to build a telescope which is about 30 kilometers across. Now, you cannot make that out of one piece of steel. It's too expensive, and it would collapse under its own weight. So we have a trick for that, and that is interferometers. So on the bottom right, you see a very fast movie of the Westerbork telescopes dancing around the sky. We bake a telescope as big as 3 kilometers in diameter by putting the 14 telescopes in a row. This never happened during the rehearsals, of course, but now my movie here in the bottom doesn't play. That might work. Okay. So what happens in this interferometer is displayed at the left top. Rather than having one parabola focusing all the radiation into a single point, we are going to simulate the entire parabola surface by having all these telescopes in an array and doing the different paths to get the stuff into focus by digital processing. And there's another advantage to this, because if you bring all the signal into focus, you have one pixel, and a focus point of a radio telescope usually only has one pixel. But now, with this interferometer, we can also figure out what the signal is at a small angular displacement by having the signal added up in another phase. And if you have been paying attention in your mathematics class, you will not be surprised that such an interferometer is picking up the Fourier components of the image distribution on the sky, and with doing a two-dimensional Fourier transform, you can calculate back what the sky would look like. Okay, so if we can do this over 3 kilometers, we can do this over 100 kilometers, and we can do it over 1,000 kilometers. These are the telescopes that work together as a single telescope in the European VLBI array. So it spans all the way from Finland to Spain, and in fact it goes on because we also have a telescope participating regularly in South Africa. And from Arecibo in the Caribbean all the way to China. Depending on what the astronomer wants to observe, he will make a selection from these telescopes. The central heart of this telescope is in Dwingelo, in my institute in Jive, where we play back all the signals from the telescopes after the observations. Here on tape, but nowadays it looks more like this because we have switched to hard disk recorders. So the principle of VLBI is you select a frequency band. All the telescopes look at the same part of the sky at the same time, which of course means a different part of the sky because we're all on a spherical planet. And using the same frequency, they digitize a little bit of the spectrum. They write that on a magnetic medium together with in very accurate time measurements. It's shipped to this supercomputer where all the signals are perfectly aligned, and we're trying to detect the common electromagnetic radiation that has hit these telescopes during the observations. So, fortunately, this one does work. Great. So, and this is one maybe not very typical, but at least a very exciting result that you can obtain in this way. So let me first explain what you see here. This is a very small patch of the sky, from left to right and from bottom to top. And at every pixel, we register how much radiation is coming from that. That is given in the contours. In the colors is actually how much polarized emission is coming from these places. And if I play it again, you will see that this observation is actually a set of observations about 2 years in a row in which we can see the electrons, this very hot gas, actually flow along the sky. This is a very, very small piece of the sky. We're now looking at something with more than 1 million times better resolution than Galileo did. These are milli-arc seconds, a thousandth of an arc second, a thousandth of an arc minute, a 60th of a degree. Sorry, a 60th of an arc minute, a 60th of a degree. So the size of these clouds in this far away radio source actually span the same angular size that you would have if you would put a tennis ball in New York City. That is the angle that this subtends on the sky. And what is the physics? Well, we think that the physics is that at the heart of this galaxy we are observing here, there is a massive black hole, a singularity, from which light cannot escape. And while it is eating up the gas from its host galaxy, it's making a part of it so hot that it streams out in these jets. And astrophysicists are trying to understand how these things work, what it means for the evolution of the universe, etc., etc. Here's another movie. And we're watching the explosion of a star at the end of its life. This is optical. We're zooming in. In 1993, this star went bang. And now we're following with radio emission, again with VLBI, the expansion of the hot gas that came out of that explosion. This is a year after the explosion. And as this movie continues, we see the expansion. Again, it is very exciting. And at one point, the other question might be, so why are we interested in this? Well, figuring out how this expansion is evolving, how it is decelerating, gives us a clue of how the star was built up and what it has done to its environment before it went bang. And a lot of these stars are important for the evolution of the galaxy. All the heavy materials that we have for lunch, all the heavy elements that we have for lunch are generated in explosions like this. Okay, well that was entertaining, that was astronomy. So now I'm going to tell you how we have moved to eVLBI and how we're going to make the network into a telescope. And therefore I have to first tell you how we did this traditionally, how we make these images. We need big telescopes, I already explained that, and we want to record as much frequency space during these observations as you can. So we have to digitize a large bandwidth. And the typical VLBI experiment nowadays uses about 64 megahertz of bandwidth in 2 polarizations. So if you use Nyquist sampling to digitize that, you will end up with 256 megasamples per second. Now, you're typically used to recording data with maybe 24-bit depth, or if you have to be economic, maybe 8-bit depth. For radio astronomy, it's fortunately much simpler. We can show that the signals that we're looking at are so noisy that actually 2-bit depth gets you 78% of the signal-to-noise back. So fortunately, although we have to sample with Nyquist rate, we don't have to use many bits. So typical observations work at 256 megabits per second. We would like to do better, maybe 1 gigabit per second, maybe in the future 4 gigabits per second. For you, it is important to notice that a bit in this is not sacred, right? Our signal to noise will go down when we miss a few percent of the bits, but it's not like watching a movie or getting a document across where every bit is important. So how do we do this? Traditionally, we did this on tapes, and they were very vulnerable and very expensive. And only since a couple of years, it's been possible to get interesting data rates on these hard disks. So basically, we're using the same technology that's also been used in hard disk recorders you may have at home. And we're shipping these packs with 8 parallel hard drives around the world. And so they come to Dwingelo, and Martin, our operator, he has the job to continuously find back the right disk packs and put them in the correlator. That's probably why he's not looking all that happy in this movie. I hope he's not watching. So we kept having questions. Why are you doing this, shipping these disks around? Why are you not streaming the data on the internet? School children would ask us that 10 years ago, and we would say, no, that's not possible. The data rates that we are interested in, it's just not feasible. But of course, it has become feasible. The rates that I just mentioned don't scare you, your community at all anymore. So in 2004, we started a pilot connecting some of these telescopes. And connecting these telescopes really means digging. There are, of course, good connectivity in major cities and major campuses, but all these telescopes were built on purpose on places where there is very little infrastructure. To avoid interference, all these telescopes are in mountains, in protected forest, often 20 or 30 kilometers away from the nearest point of presence. This pilot project was boosted by our EC-funded Project Express, which had a few goals. First, and importantly, and very rarely visible, we had to retrofit our correlator because it was designed to play back tapes and work in batch mode. And we had to completely rework it to make it work in real time. We were going to solve the last mile problem, which often was more like 10 or 20 miles at some of our correlators. We were going to work with the NRENs on getting very robust transmission mechanisms, because a bit is not sacred, but if you miss a longer time span, then of course the whole observation is ruined. We're going to push to the 1024 megabits per second limit. That was another goal. We had to connect some of these bigger telescopes. And in fact, something we didn't realize, we also had to sort of make a cultural change in our own astronomy community. So fortunately, we are actually in a very good situation in Europe and in the Netherlands, because in Europe we have the GEON2 network, which provides very good connectivity across the states where we have telescopes. And in fact, through this European collaborations, we are now quite a bit ahead of our American colleagues in this field. Similar, we are blessed with very good connectivity in the Netherlands on the SurfNet 6, where there is now a special path that goes all the way to the woods where we live and provides us with a couple of bundles that can carry all the telescope signals. We, of course, had to build our network in Dwingelo. We have telescopes that are local, that come on dark fiber. We have telescopes that come through SurfNet, and we have a lot of telescopes that connect in Amsterdam to Zeeland. And we had to build our own connections and light it up in order to get all these connections going. And actually, the progress has been quite remarkable over the last 2 years. At the moment, we have a situation where we regularly have 6 telescopes online, which is enough to do interesting science. We have a correlator upgraded, and it now works just as reliable for internet, for eVLBI, as for the old-fashioned disk-recorded VLBI. We provide new tools for more rapid feedback, because this is now all happening in real time. And I must say also the connectivity has reached an impressive reliability. This is a graph where you see time on the horizontal axis, the data rate per telescope on the vertical axis, and the size of the bubbles corresponds to how many telescopes are participating. So in 2004, we were very happy if we got 32 megabits per second to 2 or 3 telescopes. And nowadays, we are regularly quite close to a gigabit per second with 5 or 6 telescopes. So here is a table of our connectivity. And you can see there are quite a lot of different ways of connecting. We are very happy when we have light paths to the telescopes that participate. This gives us the best undisturbed connections. And you can see we have most of the European telescopes on light path. And of course, Westerbork is so close, we have a dedicated dark fiber. You can also see that the connectivity is uniformly about around Europe at 1 gigabits per second. And this is a status figure that shows the quality of our light path. And so most places are up very reliably, and we can switch on our eVLBI system almost any time. Some of the light paths that are discontinued, you don't know, of course, because you don't know where Parkes is, but that's a telescope in Australia with whom we did some experiments. But there's really no scientific need to have that light path up all the time. Recently, we have made a big announcement, because for us, this is a very big event. This is the joining of the 100-meter telescope in Effelsberg. In Germany, in the German Eifel, this telescope was particularly hard to get a connection to, and it really involved digging 30 kilometers of trenches through a rather mountainous environment. So it came online on the 1st of April 2008 with the local loop provided by the Max Planck Gesellschaft that also owns the telescope. We're very happy that in the first test it got all the way up to 1 gigabit per second. For our users, for the astronomers, this is extremely important. This telescope with its 100-meter diameter and its high-frequency capability sort of doubles the capacity of our science instrument. So that is one recent result. Another recent result is that we are pushing the sensitivity limit to 1 gigabit per second. So these color diagrams that you see all the time, they display time, and every color is the incoming signal block from a specific telescope. And there on the top one, you can see that we now are able to fill the 1 gigabit per second lines almost with 1 gigabit per second data rates. And that is the maximum sensitivity that our current equipment can obtain. Also very significant for us is the bottom graph, which shows that we can do this sort of sustained over 24 hours. And the only gap you see there in the middle is when we actually switched from one user experiment to a next user experiment. So not only are we getting to very high data rates, but we're also getting to a very reliable regime. And for us, the reliability is very important. So that allows you to do the real science runs. And it's also operational very important, because these science runs run for 24 hours. So we have to man the correlator overnight. And as you can see in the bottom movie, it can now be done by one postdoc, although he has to run around quite a bit. And as I said earlier, I think I can skip over this mostly, we also had to retrofit quite a lot of our software to make sure that the correlator worked in real time. So this is Europe, basically, and the demo that we do today, up there in, I think it's the Bach room, is actually about global connectivity. Because in Express, it's not just these 7 or 9 telescopes in Europe, but we also have participants from South America, South Africa, China, and Australia. So when I started this project, I was quite skeptical about how you would do this. And the reason was that at the time we were doing TCP/IP mostly because our equipment was outfitted with rather old Linux kernels. And with TCP/IP, getting connectivity in Europe was okay if you had more than 2 times the bandwidth than your data rate. But across the globe, of course, it was a no-go. Anytime you get any sort of congestion, there would be a round-trip time of so many milliseconds that the whole thing would clog up and fall over. Last year, we were able to switch our transport protocol to UDP, and that allowed us to get much better response on these very long stretches. And the first demonstration of this we did last summer with our colleagues in China. And for us, China is very important. It's a booming country in all respects, and also in radio astronomy. They used to have one telescope at Shenzhen and then one in Urumqi. But given the fact that they now have a lunar program that requires more radio telescopes, they actually have now 4 telescopes, and the one in Miyun is actually much bigger than the other ones. So we were very happy to collaborate with the TN2008 program to get Chinese data across. And I think we made a very strategic move to go there to the telescope and get the Chinese involved in a demonstration that was successful last year. This is the throughput of that experiment, and these are the so-called fringes. Well, you've seen these before, but I still haven't explained what they are, so let me try to do that now. So when we look at the sky, we look at, all the telescopes look at one radio, the same radio source. The radio source is only a very small fraction of the signal that both telescopes see. It's dominated by the noise from the atmosphere and the sky. So these are so-called correlation functions, and on the horizontal axis are the different retardation, the different delays with which we are correlating the signal. And if everything works perfectly, we expect to see a small amount of correlated signal at the perfect delay, where we have delayed the signals of the 2 telescopes with exactly the right amount. Away from that special timing, the noise of the 2 telescopes is uncorrelated and it just vanishes in our integrations. But where we see where we correlate the exact radio source, you get this spike. So we are always very happy when we see these spikes. They're called fringes for the reason that in time they will vary, and on paper recorders they used to look like kids scribbling a fringe, and they're still called that way. So that was our first demo with the Chinese. We soon did also, or we did at the same time, the first demo with the Australians. And in fact, we did something even more fancy with our Australian colleagues. This is the throughput of 3 telescopes sending their signal into Dwingelo. We have this map on the wall with lights for all the telescopes that participated. And my former boss was an Australian, and he put lights in the Australian continent, and we all joked that they would never be lit up, because this has very little common science with us. But in fact, they did that day. 3 telescopes sent their data to Dwingelo to observe the supernova in the Magellanic Clouds, and we produced this science results, which is in press, by using the Australian telescopes and the European correlator. So that was last year. What we're doing today is to work with a network which is as big as this. So more telescopes have joined. You can see the Effelsberg telescope has joined in Europe, but we're also depicting a connection to Hartebeest Hoek in South Africa, to this funny-looking antenna in Chile, and to the big dish in the Caribbean. So so it's always very important to make sure that you understand where this is all, how this is all coming about, because it involves a large number of networks, and we are fortunate to have friends in many places. So, for instance, to get the data out of Puerto Rico involves about 5 or 6 different organizations. So these are these telescopes. Unfortunately, I couldn't find the pictures with the right day and night, because in South Africa, to the right bottom, it is actually daytime, just like here. But in Arecibo and in Chile, people got up really very early this morning, not only at the telescopes, but presumably also at the NRENs, to make today's demonstration feasible. So when you go upstairs, you will see computer screens like this. This is at Dwingelo, where we monitor the progress of our experiment. And just to make sure that you know what you're looking for, these are the delays again with the spikes. If we see the spikes, the people upstairs can tell you which telescope pair they are, and you can see for yourself that it's working. And just to make sure that you really know what you're looking for, I've included also this picture. This is a happy astronomer who gets a positive result. So please look for that upstairs. So I've told you now how it works. I'm going to tell you why it is important. So these are the very simple images we were able to make with a few telescopes. And if you add more and more telescopes, you can look at weaker and weaker sources, but not only weaker and weaker sources. You're collecting more and more information about the sky, so you're also able to look at more and more complex structures. And this was our first science result last year. And what is specifically exciting about eVLBI is the ability to have your response, your scientific output, immediately after the experiment. Before, people would write proposals, observe a part of the sky, wait until the tapes were shipped to Dwingelo, wait until it was all the tapes were there and correlated, and then at their leisure would look at a part of the sky. This was okay for a large part of VLBI science, but not for everything, because you've seen it before. Sometimes stars just explode, and you, of course, don't know when that's going to happen. So eVLBI is extremely suited for that sort of science, where we have a star exploding, and this is a much closer galactic black hole candidate that every now and then eats up a bit of its surrounding gas, and then it will flare up, and at that point astronomers would like to have a look. So that is one of the goals that we have in eVLBI, is to shorten this time from knowing that something's happening in the sky to getting to a publication. So that is one, and at the moment, our most important motivation to go to eVLBI. You get this fast response. You can immediately see whether you're doing something interesting. And you can, in principle, adapt your observing parameters. At the moment, that's important, and we think in the future it's going to be even more important as many more astronomical instruments are coming online, which are specifically designed to do rapid response science. Another advance is that we can see that now already, is we get immediate feedback on the data quality. Before, when we used recorded signals, we would find out a month later that some telescope had put a wrong cable in. If that happens now, we know it immediately because we can check the results with the EVLBI directly. In the long term, I think it's also important that we will have fewer consumables and fewer logistics. Rather than having these specially arranged VLBI sessions, I hope we are moving towards a continuously available VLBI network. And there's one application where that is of extreme importance. 2 years ago, we demonstrated that VLBI can also be a very useful technique for monitoring spacecraft. This is the Huygens lander that went on Titan, one of the moons of Saturn, and radio astronomers were able to track the signal with Earth-based telescopes, where the NASA had originally planned that it would be relayed by the orbiter around Titan. And not only did we have immediate feedback on the condition of the spacecraft, we were also later able to calculate back with very high accuracy, about 10 kilometers, what the trajectory was when the thing went to the surface on its parachute. And in fact, this has created quite a lot of interest with planetary scientists, and VLBI and JIVE in particular is featuring in 2 of the proposals that the ESA has currently under consideration for its next missions to either Saturn or Jupiter. One thing that was a bit of a struggle, to my surprise, is that we also had to make sure that we were initiating a cultural change in how VLBI is done. We have a peer review process where telescope time is very expensive and is only given out to people that have put in a very well-motivated proposal. And this system sort of prohibits initially to react to some things that are transient phenomena and go off on a daily basis. I think we're now in a situation where we've remedied that. We have several methods where people can indicate what kind of triggers they are going for and what kind of conditions they want to do EVLBI on. And in fact, we have also a much more liberal target of opportunity a proposal mechanism, and that resulted, for instance, in this astronomical telegram, which is a means of communicating that something is happening right now. Here is a perfect example of an EVLBI observation we did of that. This is another supernova, another star exploding in a very, very far away galaxy. And with the EVLBI, we had not only the resolution, but also the sensitivity to follow this up immediately and tell the rest of the astronomical community where this was happening and how much gas and electrons were involved in this explosion. And this is a very recent result where somebody said, well, if the X-ray satellite BATSI is going to see a flare, then we would really like to follow that up in the radio. And this happened last April. And these are very preliminary maps, so I'm not going to try to convince you that they are very interesting, but I can assure you they are, of that event. Now, in the last 10 minutes, I'd like to show you a bit about our R&D efforts and where this is going. Part of our Express program also is has a joint research activity which is looking at going beyond this 1 gigabit per second. Our data acquisition systems at the moment were designed for writing tapes at 1 gigabit per second, and getting them beyond that really requires new samplers, new digital equipment, and new ways of getting this data out onto the internet. And we're working on these FPGA boards at the moment to make sure we can do that. Similarly, we also have to look at upgrading the correlator. So the supercomputer that does the comparison between all these signals and finds these spikes is really based on a very simple single chip, but it runs 1,024 of these chips in parallel. We think that in the next decade we will see the requirement for boosting the correlator capacity by a factor of 100. Now we could probably implement that on normal supercomputers, but we are looking at something which is getting quite close to the petaflop regime. Well, in fact, the operation we want to do is rather simple. So we're trying to figure out other ways of doing that. And one of the projects in that was presented in session 3A by Damien Marchal, where we are trying to see if we can deploy this correlation in a much more efficient way by spreading it out geographically, much like the telescopes are also spread out geographically, and doing the correlation in a distributed fashion. And this was also part of a demo we showed yesterday. And this software correlator has already produced some, for us, very interesting capabilities. We're using it now regularly to verify that all the telescopes don't have their cables switched and such things without imposing on the hardware correlator that is doing the real scientific operations. Another exciting thing for us, but not so clear how we're going to connect it with EVLBI, is this concept of an orbiting telescope, which makes the resolution even larger than the resolution limited by the size of the planet. The Japanese are designing this spacecraft, and we are looking at ways to enhance our correlator to make sure we can also play along in this game. That was the first. That is something on the shorter horizon. It is quite clear that radio astronomy is facing another revolution, because so far we have done radio astronomy with few big telescopes, because our computing needs scale with the number of telescopes squared, and they were always prohibitively large. So you put all your money in making the steel making the steel part as big as possible. LOFAR in the northern Netherlands is an example, although at quite a different frequency, of a different concept, namely building as many as possible very simple telescopes and connecting them in real time with a lot of connections and many more baselines in computing to do. We are positioning ourselves with EVLBI to pioneer the connectivity requirements and the computing requirements of that square kilometer array, which is going to be placed or built either in an Australian or a South African desert. Okay, before I end with my conclusion, maybe it's good to check up on how the guys with the demo are doing. All right, well, that's really very, very impressive. So the fatter colors are respectively Onsala in Sweden, purple is Effelsberg in the German Eifel, Medicina is in red, it's near Bologna in Italy, Westerbork is the aqua color in the Netherlands, and you can see that during my speech here, the data flow into Dwingelo has been quite continuous. And the really impressive thing is the three colors on the top. Although Hartebeest Hoek in South Africa in yellow and Tigo in Chile by design have a smaller bandwidth, the reliability of that connectivity is really very impressive. And Arecibo even comes in with a European-like data capacity. I think for safety, this is the fringe, so the spike on the short baseline to Effelsberg and Westerbork. But I'm quite sure that if you run upstairs after the session and catch this in action, you will see the first time ever detections in real time of radio sources between all these four continents. Can we get out of this? Okay, so ending up with my conclusions. In the course of this project, we have achieved the fact that EVLBI is now an operational, a robust astronomical facility in Europe. It's enabling new science, and I think the best is still to come now that we have the, for instance, Eftelberg telescope online, and we can go all the way to 1 gigabit per second. We are extremely happy with these light path connections that we have established with many of your NRANs around Europe. It seems to be extremely reliable, and when it works, it really flies. Quite a bit to my surprise, we've also demonstrated in this project that we can do intercontinental VLBI this way, and that opens up a whole range of possibilities for the future of radio astronomy. And I think I'm very much convinced that EVLBI is a growth path for getting radio astronomy, or VLBI in particular, into a much more sensitive domain by transporting larger bandwidth. So, although the project is only slightly more than halfway, we are thinking much about what we want to do to make that promise even more, get even further with that promise. So one of the things we would like to see develop in the network community is light paths that are controlled more dynamically, especially for a distributed correlator project. That is something that is highly desirable. And it doesn't stop in Europe, right? So you are encouraged to make sure that all these mechanisms are globally implemented or available. I think we also have learned that if you want to do stuff like this, you really have to get into a project and work very closely with the NRANs. I think that is the basis of our success, is this, and in fact, credit to the EC here, this EC imposed collaboration scheme, which really has worked out very well. And I hope to be able to do 10 gigabits per second VLBI and really make my fellow astronomers forget about how they used to do this with tapes and discs. That is what I would like to see from the networking community. There's a couple of minor points at the bottom that our community has to solve, which is about getting new correlators, making sure we have a similar system in the US, and find out the synergy with the development of the SKA. So by showing you the logos of all the participants in Express, I hope, I'd like to thank you. There's time for some questions. Okay, there's time for some questions. Ah, there you are.
Yes, it was on your wish list on the last slide to do something more with the US, and I noticed in all the previous slides and maps of the world that the US, except for Puerto Rico, was missing. Can you tell us a little bit what the problem there is, why they're not on board yet?
Okay, so the VLBI network, the dominant VLBI network in the US is run by NRAO, the National Radio Astronomy Observatory. Well, first of all, the US funding schemes don't allow for a collaboration like we have been able to establish in Europe. And the NRAO, as many US science facilities, is under a lot of pressure, financial pressures. And their focus at the moment is to finish their collaboration in ALMA, which in Europe is dealt with by ESO, so it's out of my domain. So yeah, it's basically an issue of political climate. They're very eager to move forward along with us, and I had the discussion with them 2 weeks ago on how we're going to make a common plan for the future. But yeah, I think by the the political arena in Europe, we've really left them behind at the moment.
Are there any more questions? If not, then thank you very much again. I need that. I will need. Yeah, I have some slides now. Okay, ladies and gentlemen, let me now share with you some closing thoughts. There are still some thank yous and farewells to say, and of course some announcements for the future. Let me remind you that Terena organizes an annual networking conference with the main goal and to provide the opportunity to all of us to present the results and discuss the issues and challenges, current ongoing projects. These events bring together the NRNs and their constituency, the academic research and educational community with industry and policymakers and governments. Having seen all of the sessions full with people and seeing lively discussions during the breaks, I think I'm entitled to say that this conference was a success. This year's TNC was hosted by Belnet and local support provided by Event Mosaic. We were close to 500 participants, and that is a record for Terena conferences. We had 104 speakers in 4 plenary sessions and 33 other parallel sessions, number of side meetings, workshops, both demonstrations, one of them still going on. As you know, the title of this conference was the Beyond Connectivity, and aside of regular providing the topics, this year's program committee decided to put some questions and seek for the answers. So let me remind you, we were seeking for the answers on who's there, is this for real, what's bothering you, what is behind, what's happening, what's next, and finally, last but not the least, who cares? The users do, they say. And let me remind you, last year we were invited to make a kind of comparison between our system and the ocean, because both are quite complex. And this year it looks like we are developing a taste for extreme environments. This year we were invited to think about the layers. And I'm borrowing still from our keynotes. We were asked to who's there. As you could see, this is a digital party. This is borrowed from one of our speakers, and it looks like we have some uninvited guests there, or unexpected, better to say. And furthermore, some of our keynotes provide us with a number of questions, like, do we really prefer functionality to quality? It was more than a statement than a question. And are we building tomorrow's networks for yesterday's world? Do we need a new business model, at least in NRNs? And we should definitely look beyond layer 7 if we are looking beyond connectivity. As I said, I think I'm entitled to say that this was a successful conference, and you will share that, and that you are sharing that opinion with me, and therefore I would like you to join me in thanking the program committee who set up such a nice program, and the program committee was chaired by Diego Lopez from Red Iris in Spain. So thank you guys very much. Nevertheless, I would like to thank some other people also. All the speakers and session chairs for their hard work, for their time, and for sharing their results and work with us, especially to plenary speakers in the order of appearance, Paul Van Beens, Josh Howlett, Stephen Hanna, Tim Robinson, Richard Katz, and Hubjan van Langevelde. Finally, last but really very important thing is thank you all for coming here, for being a part of the conference and sharing your thoughts with the speakers. Of course, this should work better, or I should learn how to use it. Of course, there are some more people we would like to specially thank, because they were not here to attend the conference. They were here to provide us with a venue. I'd like them to join me here at the podium first. Verle Kasters, who was in charge here from Belnet and in charge of the organization staff. Thank you very much. Jan Mas, who was in charge of technical support, and he won't get any flowers. Julien Lamoral, now things are getting hard for me. Ludovic Grutardia. And now to somebody who is not from Belgium, rather from Belgium Science Policy, and was in charge for our audio-visual part, David De. Sorry, David, I can't pronounce it. But thank you very much. Steve Ross from Event Mosaic that provided our local support, take care about our social events and hotels and all the stuff. Carl Polen from Cardinal, our caterer. And one definitely should not forget about the Terena Secretariat, who was working hard for more than a year on this conference. And I'd like here especially to thank to Genji Horvat. This was her first conference, and it was not an easy task to take the leading role from Karol de Groot, who is still here with us, but still Jonji managed it. And so thank you, Jonji, and hope to meet you in more closings in the future.
Thank you.
Yeah, I'm not finished. Last but not the least, one should thank to our sponsors who made it possible, who provided their services in order to make this conference a success. And the main sponsor was the Belgacom. Yeah, we have to continue further, and the next conference will be in June this time, a little bit later, in Malaga in Spain. And I'd like first to present you the program committee for the next year that will be chaired by Andrew Cormack, and eventually you will see it at the slide number 13. That might be a problem because this is the slide number 13. So here it is. Thank you, guys. So the next year program committee will be chaired by Andrew Cormack, and you see the setup of it. And without a further delay, now I would like to give a floor to our hosts, next year hosts from Red Iris and University of Malaga, Thomas de Miguel from Red Iris and Victoriano Giralt from University of Malaga.
Well, it's a pleasure for me and for Victoriano to have the opportunity to invite all of you to the next Terena conference to be held in Spain and, as you see, in Malaga the next year.
So, first, a few words about our city, which I would like you to come and see. It's a city with a long, long life. It's been living over the centuries from the times of the Phoenicians up to these moments. So it's been a lively city changing and always changed and keeping good things. So we have very old traditions due to this long life, and these traditions have been mixing lots of cultures, and those cultures have been producing some interesting things, and these have made us perfect hosts, I may say. Many people come down there and enjoy us. So, back? No. Should be going back. Yeah, perfect host. Okay, and then...
Well, the conference will be in, as you see, in a perfect collaboration environment, which is the University of Malaga, which is a place which allows us to enjoy the university environment. And it's a place which is quite near the Andalusian Bioinformatics Center.
And it's very easy to get there. We have lots of flights coming into Malaga from all over the world, I may say. Most of them coming from the big hubs and the small airports of Europe. So it's very easy and many times cheap if you book in advance to get to Malaga. So once you get there, you have a whole gamut of choices for staying. You can stay, that should be changed. There's a whole gamut of choices, so you can stay, depending on your budget, in very, very nice places.
Yes, we are working now very hard in order to pursue the perfection in the next, during the next conference. And of course, with the help of those that preceded us in the organization of the conference. Thank you for all of them.
So, I think you better see it for yourselves, and here we go.
Terena, Red Iris, and the University of Malaga invite you to join us in Malaga for TNC 2009. Malaga, a city that has known how to welcome visitors over the centuries. Phoenicians, Romans, Arabs, all came to our city and even stayed so long that some had to leave. They left unwillingly, but they left behind their taste for a relaxed way of life and healthy food. Nowadays, Malaga receives millions of visitors a year that arrive through a very well-connected network of transportation. The third greatest airport in mainland Spain, the high-speed train, cruise boats, and their own vehicles. Malaga, a city with lots of things to enjoy. One of the best climates in Europe. Wonderful beaches. Gorgeous golf courses. A varied and healthy gastronomy. But also a great many options to feed our appetite for culture. Museums. Art on the streets. Old buildings, remnants of its past and its visitors. Some of the visitors coming to Malaga are not tourists, but students and researchers that come to stay in our thriving university. A university with close to 40,000 students. A 3 million square meter campus, and all the modern facilities you would expect of a 21st century university. Including one of the nodes of Spanish National Supercomputing Network in the Bioinformatics Center. a university connected to RICA, the Andalusian Regional Network, that connects to Red Iris, the Spanish National Research and Educational Network, and through Gayant to the global internet.
Ci vediamo a Malaga al TNC 2009.
On se voit à Malaga sur TNC en 2009.
See you in Malaga for TNC 2009.
Terrena, networking the networkers.
So, if the video... If the video has not yet whet your appetite for Malaga, you should better get trained to come to enjoy our gastronomy. And for that, we have brought with us samples of extra virgin reserve olive oil provided by one of the, I should say, the best company in Spain that produces olive oil. So, there's been a small glitch in the transport, so there are not enough of both of them, so you can select between salads special with a dark top or breakfast special with a light top. Okay? They will be provided when you go out, and you can then train your taste buds to the Mediterranean diet with your samples.
Well, this is only to test a little bit of you can see there in Malaga. So we want to see you, all of you, there next year. Thank you.
TNC. Don't forget to bring family and friends.
Ladies and gentlemen, it was our closing talk. For the further information about the next year's conference, please check the website. And have a safe trip home. See you next time in Malaga. Thank you very much.